All right. All right, so we're going to, in chapter 12, we're going to, kind of throughout, chapter 14, vectors don't show up really at all in chapter 14. We'll put vectors into integration in chapter 15. But vector-valued functions and then another kind of vector function in chapter 15 are going to be our main tools. I just want to kind of recap the kinds of functions that we've talked about so far. So our normal functions that we've talked about since algebra are explicit. And explicit functions are something like y equals f of x. You plug in x and you get a y. So every x value then gives you a y value. So you get for every x value you get a coordinate in the plane. We haven't done a lot of work with them. We'll work with them more in chapter 13. But in Calc 1, you do a little bit of work with implicit functions. And that's some f of x, y equals a constant. So in Calc 1, you talk about implicit differentiation, where you have some x squared y minus y xy over xy equals a constant, and you have to find dy dx, for example. We'll talk more about these implicit functions and what they have to do with surfaces, and we'll talk more about those in chapter 13. We've also talked about parametric functions. So that's where we have x equals some f of t, y equals g of t, and we could also have a third z equals h of t. So I'll just do these two things. So parametric functions, for every value of the parameter, we get a point in space. We get, for a parameter, we plug in a parameter, we get an x and a y. We get a point in space or a point in the plane. The parameter, usually we think about the parameter as time. Doesn't necessarily have to be time. It can be, our parameter could be an angle. One of the important parameters that we'll talk about this semester is arc length. We'll parameterize things in terms of arc length. And we'll see later in this chapter why that's useful. So today, and for vector valued functions, I'm going to use abbreviation so we don't have to write it out, VVF. So today we're going to talk about vector valued functions. What we're going to do with vector valued functions is use the components. We're going to use the parametric equations, our components in parametric equations, to be the components of a vector. So we're going to say something like r of t is f of t I hat plus g of t j hat plus h of t k hat. And we're going to jump straight into 3 dimensions. So every value of the parameter gives us a position vector. We call this a position vector. And our parametric equations, f of t, g of t, h of t, give us our components. So we plug in a parameter and we get a vector. As t varies, the tip of the vector is going to trace out a curve in space. I'll draw a picture here in just a second. So instead of parametric equations, an x and a y and a z, instead of a point, we get an arrow that points to the point in space. And that arrow, as t varies, that arrow is going to point to different points, and we're going to get a curve.
And then the initial point doesn't matter.
We think of the initial point as the origin. But yeah, since we're talking about vectors, in this case, t equals 0 is the origin. So let's draw a picture of that kind of visual that I just did with my finger. So we get a vector that points to a position in space. T is going to vary. So we'll get something that looks like here's our coordinate system. And we'll get, I'll draw some vectors here. I'll make those blue, and I want to make those like that. So let's say that's R of T1. And I get another vector over here, R of T2. And a third vector over here, R of T3. We could keep going. If we connect these, the tips of these vectors, and do that in blue. We get some kind of curve in space. And we could say this is directly above the x-axis. We could say this point is here, this point is here, something like that. And this curve is going to be our curve C.
It's always a curve, it's never a plane.
It could be a plane. Well, our vector value function could define a plane.
Okay.
But if we could think of what we're thinking in this case is we're going to get a two-dimensional curve in three-dimensional space.
Okay, so it's always 2D.
Right.
At some point.
And the domain of our vector valued function is going to be the intersection of the domains of the component functions. So F, G, and H. So F, G, and H are some, F is T, and G is T squared over T minus 1, and H is natural log of T. Wherever those three domains intersect are going to be the domains of the vector valued function. So you have to be able to plug your parameter into all three component functions. So what we're interested in today mostly is one is the concept of a vector valued function. We're going to talk about how we visualize them. So let me and we're going to use a technique, tools that we use in chapter 11 for our three-dimensional surfaces. So let me grab a couple of things here. I want to grab some pictures, and I want to start up Mathematica. So there are my pictures. What we want to do in this for these pictures is we want to match the vector valued function to